Assalamualaikum warahmatullahi wabarakatuh. So welcome back to our video. So this is chapter number 5 on the topic of single line diagram and some of the learning outcomes. Whereas the end of the chapter, you must be able to first explain basic arrangement of power system components in an electrical installation or an electrical system from its single line diagram. So basically, there will be no much explanation on this subtopic as assignment has been released and has been assigned for you in order to complete by groups. So perhaps by having those discussions, it may help you in order to have a better understanding on how the SLD should be arranged and should be learned. And then for the second point, so you must be able to calculate and the required ampere size for the distribution equipment necessary for an electrical design. So this is what we are focusing on for this particular chapter. So you must be able to calculate the currents, all right, the ampere size for the distribution equipment. For example, for motor, we have transformer, we have bus bar, we have the capacitor bank, etc., etc. We will see later on. And then the third part also, this is similar to what I have explained in point number 1. So these two are interrelated. So you must be able to draw the single line diagram of electrical installation or an electrical system based on the given requirement and criteria. So these two somehow has been assigned as your group assignment. Introduction, power system are three-phase networks. Each component is, yes, three-phase, and each power circuit consists of three conductors. So this is basically what we can understand from the three-phase networks. We do have the components of three-phase as well as the three different conductors. Okay, a complete conventional diagram showing all the connections is very complicated and impractical. So this is what the SLD is all about. So it has the complete conventional diagram for the initial engineering or power system field. So where the connections, it is actually complicated and impractical. But somehow for three-phase system, so we do have the balance system and are generally operated as a balanced three-phase system. So this is how the idea of single line diagrams coming out. So it is a concise way of communicating the basic arrangement of power system components just using a single line or one line to represent all three phases. To say this is much easier in order to understand the operation of the system when we are having the one line or single line diagram. Okay. Then in single line diagram, standardized schematic symbols are used to represent all components of a power system. So we have example of circuit breakers. So we have transformers, capacitor, bus bar, conductors, generator, etc., etc. So by the way, all these components are represented in a particular symbols which have been accepted all over the world, especially in ethical engineering study. So again, SLD or single line diagrams are otherwise called one line diagram or OLD. Alright, this is some of these symbol, for example, okay, but there is no universally accepted set of symbols used for single line diagram. Somehow these are the symbol we could easily understand when we go through component like generator. Alright, so this is a solid symbol for a circle with line, with a horizontal line, for example, and then we do have the bus bar. Okay, this is a bold straight line again. Okay, it can be horizontal as well as vertical. Then we do have the power transformer, two windings. It can be in this coil symbol over here or two circle over here. All right. And then the current transformer to measure the current. So a straight line with these two turn off or coil. All right. By the way, there is no universal symbol which is accepted worldwide. So it depends on the manufacturer as well, and somehow it is actually can be easily understood by all the members of electrical engineering field. So again, another example of components. So we have PT or potential transformer, measure the voltage. Okay, we do have again coil symbol or the circle symbols. So the breaker, so it can be this box symbol or box with cross inside. And then the accelerator, this simple switch, for example, or we can have both combination, okay, with between these two, circuit breaker with oscillator. So in between we have the CB or the circuit breaker and the switch, the oscillator switches in side of at the side of this circuit breaker. Okay, so a bit on the oscillator nodes. So what happened in substation, it is often desired to disconnect a part of the system for what? So this is for general maintenance and repairs. So this is what happening in substation. So it is required general maintenance and repair. So from here comes the oscillating switch or oscillator. So what's the meaning of oscillator? It's essentially a knife switch and is designed to open a circuit under no load. So in other words, oscillator switches are operate only when the line is which they are connected carry no load. So when there is a no load, so the oscillator switch is operated. So for example, consider that the oscillator are connected on both sides of a circuit breaker. So this is what we have seen in this particular symbol. So if the oscillator are to be open, so this CB, the circuit breaker, must be open first. So this is the procedure on how to operate the oscillator. So you must make sure that the CB must be open first. Okay, before we can disconnect or open the oscillator. So what if an oscillator is opened carelessly? So when carrying high current, the resulting arc easily causes flash over to the earth. So it may cause a spark, an arc, or which causes a flash over to earth. So this is the risk if you don't follow the procedure properly, or you operate this oscillator carelessly. So this may batter the supporting insulator and may even cause a fatal accident to the operator, particularly in the high voltage circuit. Right. So this is somehow the reminder whenever you deal or you operate with isolator. All right, especially the knife type of switch or oscillator. And then, additionally, it is often necessary to identify the grounding connection or whether the device is Y or data connected. So you must make sure the device, the generator, for example, the transformer, for example, so this is the generator or this is the transformer, for example, is either Y or delta connected. Okay, so figure 2, identification of Y connected generator or motor. So solidly grounded, so you can see the symbol of ground over here. So this is a Y or star configuration. So it is solidly grounded. P grounded through and inductance. We have a certain number of turn of coil over here. So it is being grounded from the Y or star into the earth. So some purpose, some objective of the appearance of the inductance over here is actually to reduce the short circuit current, the magnitude of short circuit current that caused by the failure of one line to ground. So let's say we have three lines over here. So we have the third line, which is failure, and it goes to, so let's say the symbol is fail. So we have failure which goes to ground. So the, what they call it, the existence of inductance over here is actually to reduce the current I, okay, I, let's say we name it as I fault, or the third current following in the third line, which is flowing down to the earths through the inductance. And this inductance, okay, right here we can represent again here. So we reduce the magnitude of the short circuit going to the ground. Okay, and then we can also have the transformer, which is identified as being delta Y with the Y side solidly grounded. So we can also have this type of connection for the transformer for the delta star, where the star configuration is being grounded. Okay. Example, single line diagram of a small three-phase power system. So how to actually read from this figure? So the title, figure 3, three-phase power system represented by single line diagram. So basically this is the generation side. The symbol of this circle, it can be a generator, all right, on the left hand side of the figure, or symbol of motor at the right side of the figure. Mean for the at the right hand side of the figure. Okay, M1 up to M4. So this is where the generation side generating the electricity and comes to the current consumption of the load. Okay, the consumer, we can say the consumer region or consumer part. And of course, in between, we do have some transmission, distribution, etc., etc. And this is again transformer, right? So generator 1 and generator 2 as well generate 13.2 kilovolt, and stepping up by this transformer right, up to how much? 66 kV. So this is obviously a step up transformer. And we do have the sending end bus over here at rating of 60 kilovolt. So this is where the transmission is taking place. And we have the again the part and then the end bus, which is the receiving end bus at operated at 66 kilovolt. And we do have again the step down transformer, all right, over here 60 kV down to 12 kV, and this is but another bus bar over here, and this bus bar is connected to multiple machine or multiple motors with operating voltage of 12 kilovolt. So what happen if we do have a different rating voltage other than 12 kilovolt? So it's just simply put or add in another step down transformer rating from 66 down to 70 to meet the operating voltage of the motor, namely M5. Right. So this is how you can actually understand the simple single line diagram, for example, of a small three-phase power system. So basically, these are all three-phase, and of course, we do have the three lines over here. We do have another three lines over here. Okay, since this is a three-phase transformer, so this is a three-phase machine or three-phase motor, three-phase generator, but all these have been represented by single line diagram, all right, to avoid any complexity. All right, so it's much easier for us to well understood the operation of the network. And then again, so this is another typical example or typical 11 kV 415 volt substation at the distribution site. So we start with incoming of 11 kV. So we have the first circuit breaker, the vacuum tap. So we have a CT, the current transformer, to measure the currents, right? And then we have the first distribution transformer, which is stepping down silver 11 kV down to 415 volt, and we do have the second circuit breaker for safety purpose, the A type or A circuit breaker. So this is again the vacuum circuit breaker, the air circuit breaker. So it is based on the what do you call it, the application of the circuit breaker, where we put it, okay, under high voltage of kV high tension or a low voltage 415. Okay, so it suits for example vacuum, so it is applicable for 11 kV, and air circuit breaker, it is suitable, more suitable or comply the 415 voltage operation. Okay, another CT in order to read the current, the rating current, and we have the bus bar over here for 415 before being distributed into several consumer. Okay, we have hostel, department, library, all the big huge and big building. Okay, for MCCB, this is a modeled case circuit breaker for the lower voltage rating. Okay, again another CT to read the current. Right, so this is how we can actually understand the single line diagram. For sure, all these are three phase. This is three phase. Suppose we have three lines, and then now we reduce into only one single line of the bus bar over here, the cable, for example, to have an easier understanding. Okay. So in power system engineering, we are concerned with the analysis of the power system down to the major loads. Okay, so this is the major load, and this will mean that the analysis will stop at the distribution system of station. We must actually analyze further down to the load of the system. Okay, so many distribution feeders attached to a single bus in a distribution substation are lumped into a single load. So this is what example. So it is actually lumped to a single load. Even though it is go to hostel, we have multiple distribution inside the hostel itself, departments, library, school building, hospital, etc., etc. Okay. When interpreting the single line diagram, you should always start at the top where the highest voltage is and work your way down to the lowest voltage. That helps to keep the voltage and their paths straight. So this is what I have mentioned earlier. So we start with the highest voltage on top over here, 11 kV for example. So we go down to the lowest voltage and to the consumer. Or you may start from left hand side. Okay, for example, at the generation, so we go to the right hand side, the consumer or the load. Okay, and then analysis using one line diagram. So assumption that the three phases of a system are assumed balanced and can therefore be assumed as a single phase. So this is what I mentioned just now. So all the system must be assumed in balanced condition, okay, before we can reduce or we can represent the three phases into a single phase or single line diagram. So assumption can be made because what happens on one of the three balanced phases theoretically will happen to all three phases, just enough if we have only a single phase. Right? Whatever happen in the single phase may also theoretically happen to all the three phases. So this makes the evaluation of the system much less complicated without losing information. So to have a further understanding, so we will see this. All right, as we will see this exercise later on. Okay, the per unit PU is also used extensively in one line diagrams to further simplify the process. In this particular this particular subject. So we will comprehensively study or learn about PU, the per unit, in the final chapter, chapter number 8. And from there, we can actually have a simpler, much simpler analysis. All right. So work example 1.0, in the single line diagram shown in figure 6, a three-phase motor draws 10 kVA. Alright, can kVA, this is for the S value, okay, the apparent value or the complex power value. So at 0.6 PI power factor lagging from a 415 volt 50 Hz source. So determine the kVA, kilovolts ampere rating of capacitors to make the combined power factor 0.85 lagging. So the load and feeder currents before and after the capacitor are added. So we are asked to calculate the value of S, the kVA, of the capacitor, all right, to cause or to make the combined power factor 0.85 lagging. So this is how we can understand the question, okay, the requirement of the question. So basically it operates at 0.6 lagging power factor. So once we insert capacitor, this is the symbol of capacitor, into the bus bar, into this particular system, so now the power factor has been increased. So this is, I try to interpret from what the question is asking for. Okay, now the power factor is now, okay, becoming 0.85 lagging. This means we are trying to improvise the power factor. All right, so the higher the power factor, the better the system. So now with operation of motor with this apparent power, okay, draw at 10 kilo VA volt ampere. So PF is operating at 0.6 lagging, and somehow after we put in capacitor, so power factor becomes better, much better, which is 0.85. The question is determine how much the S of the capacitor. C stands for capacitor. Okay, so how much of the S for this capacitor we need to inject in order to have power factor of 0.85, or to improvise the power factor. All right. So, and also we need to calculate the load and feeder current. This is the load current or motor current. So this is the feeder current. So we have to calculate the before and after we insert capacitor. Right? All right. Hopefully you are clear with the question. So solution. So power triangle may help in order to solve. We have P, we have Q as well as S. Right? We have the active power, so we have the reactive power, so we do have the apparent power. All right, so again, this is the unit of watt, this is the unit VAR, right? VAR, right? Okay, this is unit of VA, volt ampere. So remember, the basic equation for this, or the basic relationship between these three elements, we have P S equal to P J Q. Okay, VA, the unit, right? And of course, omega M or theta M, this is at cos 0.6, so the angle in degree is 53.113. So this is from question. So this is from question where we have seen that PF is given by 0.6, where PF also known as cos theta. All right, cos theta equal to 0.6. Okay, so at cos this 0.6, we will get the value of theta in degree, which is 53.13. So VA consumed by motor load is, so this is again provided in question. okay, 10 kilovar per ampere. Active power consumed by motor is PM equal to S cos theta M. This is from trigonometry theory. So we know that cos theta M, if we try to write the relationship in terms of trigonometry theory, so we have cos theta M, this is equal to PM, all right, according to this triangle. According to this triangle, we have PM over SSM. All right. What else? So sine, for example. So we try to relate between QM and also SM. Okay. So sine omega M theta M is equal to QM over SM. Okay. And then the final one is tangent. So tangent theta M. So this is equal to QM over PM. All right. So just manipulate these three equations in order to find the value of either PM, SM, or QQM. So in this particular example, so we know the value of SM, all right. So and then we know the value of theta M, and from there we can calculate the value of PM, all right, by using the first equation. Okay, this equation. So rearrange PM equal to SM cos theta M. So 10,000 okay, VA multiplied by 0.6. This is equal to 600 watt. Okay. And then reactive power consumed by motor is again using the second equation over here. Oops, yes, using the second equation over here, we might get the value of QM. All right. SM again is 10 kVA. This is from question. So theta M, just put in the value of theta M. We have calculate over here. Okay, here. This is the value of theta M. 53.13. So put it here or replace, substitute it here. So we can finally calculate the value of theta M or QM, the reactive power, which is 8,000 var. So now let QC be the var added to the system. So this is what I explained earlier. So we do have the capacitor with QC, all right, the certain amount of var, reactive power. So which is added to the system by the capacitor to improve the power factor to 0.85. So how much the QC is. Okay. So the resulting power triangle is shown in figure 8 below. So before we come up with this triangle, so it is advisable to calculate the new theta S, because we know that the system is now having a power factor of 0.85. So cos theta is now equal to 0.85. Okay. And you convert into degree theta, this is equal to 31.779. Okay, so the step is shown here. Okay, and then now the new theta S is lower, 31.79, compared to the previous one. We have 53.13 over here. Okay, so that give us idea that the new theta S, if we override on this power triangle on this previous power triangle, so now the new theta S, this is 53, so we should write somewhere here, or we should draw somewhere here with new theta S, which is lower than or smaller than theta M. So we know that the QC over here, so the QC is acting on this line on this QM, all right, QC is acting on this, sorry, no arrow over here, no arrow, so it's going down here, it's moving down here with QC amount, okay. So the QC has suppressed the QM down to QS. Let's say we have QS over here, all right, so we have the QS, all right, in line with the subscription of theta S, we have QS. So the QC we just injected, so has suppressed the QM down to QH with theta or with angle theta S, 31.79. Okay, so this is how the new power triangle looks like. Okay, the QC we just inject in here, this QC, so we just inject in that cause the reactive power to be suppressed from QM, okay, down to QS at this particular point. So how much QC is? Right? And then we need to calculate the new QS over here. Okay, since the QM has been reduced by QC down to QS, what about the new value of QS? With a new value of theta S, of course, you can simply use theta S as the new angle, okay, degree, and we may manipulate again this equation. We have tangent theta S equal to QS over PM and rearrange in terms of QS, and then we get PM multiplied by tangent S, tangent theta S. So 6,000 is the value of PM since PM doesn't change. Okay, so it's unchanged, or you can see over here PM is unchanged. We still have the PM, even though after the QC is being injected. Okay, so PM still same at 6,000 watt. Okay, the new tangent, the new theta, 31.79. So now we got the new reactive power value, which is 3719 var. Okay, so therefore, reactive power injected by capacitor is QC equal to QM minus QS. So because it comes from QM down to QS, so we have QM minus QS in order to get, we have QM minus QS in the to get QC. Okay, here, okay, QC equal to QM minus QS. So 8,000 minus 3719, so this is equal to 4281 var. Now, in order to get the load current, IL, load, L stands for load, or in this particular example, it is consumed by motor. We can simply write IM. So from P equal to square root 3 V LIL cos theta, we get load current, which is IM equal to PM over square root 3 VL cos theta M. So 6,000 over square root 3, okay, for 150.6. So this is actually the before. Okay, this is actually the before we put in or inject in QC. So this is the earlier or before we inject, okay, the initial current. Okay, because it is still using 0.6 value of power factor. Okay, so we try to make a comparison before and after we inject QC, okay, the reactive power of capacitor. So before capacitor is switched in, feeder current is the same as load current, that is IF equal to IM. Okay, so this is connected in series, you can see from here. So we have IF equal to, this is IM. All right, so we can say that before it is being injected by C, so this is open loop, this is open circuit, disconnected, so IF equal to IM. And from there, so we just simply take from IM value as the IF, the feeder current. Okay, so this is similar. So after the capacitor bank has been switched in, so the apparent power supplied by the cause is now PM, still same value. We now have the improvised power factor or cos theta, which is 0.85. Now the new value of S, the apparent power, has been upgraded into down to 7059 var over ampere. So therefore, the feeder current after the capacitor has been switched in, so this is the equation of apparent power, S equal to square root 3 VL IF. Okay, so just rearrange in terms of IF to get the value, to get instead to the value of VL, which is 415. So this is the new value of S. Okay, we obtain from here after we inject or we got the new power factor 0.85. Then the new IF or the feeder current is actually 9.82 ampere, which is much lower compared to the current before we inject or we switch in capacitor. Okay, so this is drawing 13 or almost 14 ampere compared to this only 9 ampere or almost 10 ampere. So what happened? Power factor correction capacitor work as reactive current generators. We can say that providing needed reactive power K var to the power supply. So by supplying this their own source of reactive power, so reactive power it can come from the utility, the equipment itself, from the system or from the network. But somehow in this particular example, we inject in or we switch in an outsource of or in or their own source of reactive power, which is coming from capacitor bank, for example, capacitor bank. So the industrial user frees the utility from having to supply. I mean, the reactive power is now not supplied by the utility itself. Okay, it's coming from capacitor. So therefore, the total amount of apparent power kVA supplied by the duty will be less. Okay, the S from the system will be much less. So power factor correction capacitor reduce the total current drawn. So this is another advantage when we have capacitor as the power factor correction. So the total current drawn from the distribution system and subsequently increase system capacity. Or in this particular figure, we can see a good way in order to understand how it works. So this is the utility. Let me change the color. So this is the utility, for example. This is the utility. Okay, and then B is the reactive power. Okay, the Q. Okay, is supplying to the load, the motor. Okay, this is without capacitor. So the reactive power is there and draw or consumed by motor 1 and motor 2, as well as the, of course, the power active power. So this reactive power, again, if you can understand how it works in system, is something like your a postman, for example. Okay, where postman deliver a mail from sender to receiver. So it's something like the same thing here. A postman or rider delivery for COD, for example, to bring the red one, which is the active power from utility to the motor. Okay, so without that, without capacitor, without capacitor, but with capacitor, so we have actually reduce the reactive power, the blue one here, okay, from utility. So it is now the capacity job or the capacity responsibility to supply or to provide the blue color one. The blue means the reactive power. Okay, so then the utility is now free from any reactive power. So the job has been done by or has been taken over by capacitor, and then we can have a spare active power over here. So this is the available active power, okay, in the utility. Okay, so we have actually a better capacity of the system. Okay, or else the reactive power, okay, will come from utility. So no more space for reactive or active power, the red one. Okay, here. All right, so we continue at work example 2.0, sorry, later on. And again, thank you for watching. See you in next video.